Good afternoon, everyone. Welcome to the robotics seminar. So it's a pleasure to have Nima Fazeli with us. So we are welcoming back Nima. Nima was a PhD student here at MIT with Alberto. So it's back to the future. Nima's lab has been doing, very interesting work in Michigan, related with manipulation and tactile sensing. I first met Nima when they had this, cool project of trying to take out blocks, from a stack, the Bandu image, the Jenga image that you see on a screen. So super excited to have you here, Nima,
Awesome.
and looking forward to your talk.
Awesome. Thank you very much for having me. Thank you. So today, I'm really excited to tell you about our progress on robotic tool use. And this is work with Young-Sun, Mark, and Mikkel. Before getting started, I just want to be thankful to all of my wonderful PhD students, without whom none of this work would be possible. Today, I'll be really focusing on the work of these three, Young-Sun, Mark, and Mikkel. I'm also really grateful to our collaborators at Google and Michigan, and very grateful to the funding support from our sponsors. So to get us started, tools are everywhere. If you look around in your environments at home or in the workplace, you'll see that you have a bunch of tools laying around and use them on the daily. And so here's a few examples from cooking and cleaning and perhaps performing some useful work. But the question is why? Why are there so many tools? Why such variety? And so maybe we can do some audience participation. If you look at some of these tasks, why might you be wanting to use a tool? If no one puts their hand up, I'm going to pick on people. So. Yeah, there's someone. Yeah, what do you think?
Well, for a lot of those, I actually think you don't want your hands, to get burned in the pan, for example.
Perfect. That is an excellent reason. There are really primarily two ways of thinking about this. You either want to create morphological modification. So this means you want to produce some contact, you want to transmit some forces, you want to produce some geometries with the environment that your hand is incapable of. So in this case, if you want to screw a screw, you can't do it with your fingers, but you can use a screwdriver for that. And the second reason is exactly what you said. You might worry about biochemical interactions, so you might want to protect yourself or the environment from you in some way. And so when I say tools are everywhere, I really do mean everywhere. Here are examples of tools you might see in the workshop, in surgery, in space applications, plumbing, electrics, food, woodwork. Tools are everywhere. But what is tool use? Like, how do we think about tool use? What is this definition? And so this is the one sentence that I came up with. It's prehensile manipulation for non-prehensile manipulation. And this is a bit of a mouthful, so let's walk through it. Prehensile means that which has been evolved or constructed for grasping. And so here's an example of a bunch of prehensile appendages. So the elephant's trunk, the monkey's tail, the monkey's hands even, the seahorse's tail, they're all developed for the purpose of grasping. And so they're manipulating through grasps. In tool use, what we're interested in is actually manipulating the thing that we have not grasped. So in this example over here, I am grasping the tool spatula, but what I'm really interested in is creating change in the state of the egg. That is the thing that I'm cooking. And so when we think about tool use, we're interested in the non-prehensile part using the prehensile part. Cool? This is where I expected some disagreement, but this is great. Everyone seems to be agreeing with me. Excellent crowd. Thank you. And so why should you care about tool use? Well, it has a ton of applications. So tools have applications in industrial settings, in surgery, in construction, in archaeology. You can even use these to study anthropology and even animal behavior. But in my group, what we really, really care about is assistive and elderly care. We are trying to make people be able to age in place gracefully and with dignity and respect. And so you may think about the scope of this problem. Here's a very nice chart to kind of illustrate for you how big of a problem this will be. So over here, this is an age breakdown of the US population. This is in the 1960s, right after the baby boom. So you see there's a very large portion of our society that is very young. This is projected to the year 2060. And the highlight here is that 25% of our population will be above the age of 65 by 2060. 25% of our population will be below the age of 19. And so what this means is that 50% of our population is going to have to take care of 50% of our population. That is a really big deal. It's a very complicated challenge to try to address. Is this unique to the States? Not really. Here in Europe, the trends are a bit worse. In Southeast Asia is particularly bad. In Japan, we're projected to have about 40% of the population be above the age of 65 by the year 2050. And so this is going to be a growing problem, and robotics, I feel, is part of the solution. Cool. So what are some of the characteristics of tool use? How do we think about tool use as a whole? I think it's a really interesting interplay between geometry and force transmission. And so when I say geometry, what I mean is the collection of points in 3D space that belong to the tool. The way that these points move with respect to each other and behave describes the kind of tool you're holding. A deformable tool is one such that these points move with respect to each other as well as moving as a union. A rigid tool is when they don't move with respect to each other but move as a union. And my favorite set is compliant or elastically deformable tools. These are tools for which when I apply a force, they move with respect to each other, but when I remove that force, they come back. And so what I think is really exciting and interesting and important about these tools is that they allow you to modulate contact formations, force transmissions, and deformations. They give you a lot of control regarding the contact you can make with the environment. And so they're super cool to study. So let's dig a little bit deeper. When you want to reason about tool use, you may care about the object geometry at time t. The object is going to make contact with the environment, and so here's a contact patch. You're going to have some force transmitted through this contact patch. You're going to worry about the robot actions, so these are the actions that my end effector may take, so motions in 3D space. I have some boundary conditions. These specifically describe contact boundary conditions, so where contact is being made and a type of contact, so sticking and sliding. I may also be interested in predicting the future, and so what will be the deformations of the object in the future? What will be the force transmissions to the future? And I'm going to bind all of these together with this implicit function g sub theta. The reason why we have this implicit form is to try to emphasize this fact that you cannot basically figure out one without knowing the rest. There's a very intimate connection between deformations, force transmissions, and boundary conditions. These have to be resolved together in a sort of a cohesive way. And so thinking about this one equation to rule them all, there are some interesting challenges. The underlying structure is nonlinear and discontinuous. Mechanics is hard. The action spaces of robots are often high-dimensional. You often have very high visual occlusion, especially when you're making contact. You have local tactile feedback from grasping the tool. And you want to do this in extreme variety and high uncertainty. And so this is what makes tool use interesting and quite challenging. Great. So here's the kind of system that I would like to realize in the next few years. We want to have a robot that is using a compliant tactile sensor to grasp a compliant tool to perform some useful task. And so today I'm going to show you two research thrusts. The first is going to be the compliant tool manipulation, where the tool deforms, but the grasp is rigid. In the second half, I'm going to show you the flip of that, which is the grasp is compliant. We're using compliant tactile sensors, but the tool is rigid. And we're going to see how each of these components works and how we can look into the future to put them together into full system realizations like this one. So to get us started, let's talk about compliant tool manipulation representations. Here is our goal. We want to infer and predict object deformations and force transmissions given a compliant tool in a rigid grasp. What I have access to is the set of points from this tool that I can observe. So p hat of t is a collection of points that I can see. This is strictly a subset of all points belonging to the tool. I also get a reaction wrench measure from the rest of the robot. My goal is to come up with a structure that follows this representation such that when I can perform an inference task, this means to infer the full geometry and the boundary conditions that realize this deformation. And I want to make a prediction. So what will be the future deformations and what forces will I be imparting to the environment? And so people have thought a little bit about this in the past in the context of finite element methods and particle models. And these are quite insufficient for these particular kinds of tasks. FEMs are really designed for the purpose of analysis, so they consume as input boundary conditions and a lot of physical parameters that you don't usually typically have available to you. And so inverting them and doing inverse FEM in these kinds of situations is very challenging. They're also quite unstable and difficult to do. And for similar reasons, particle models are also very poor for the inference tasks specifically. So what do? I'm going to suggest that signed distance fields are a really promising foundational representation for tool geometry representation. Here's an example of what an SDF is. Here's the famous Stanford bunny. And the idea is that I can query 3D space, and for every query in 3D space, I can tell you what is the distance from that query to the surface of the object. That is what an SDF is. And people in the past have shown how you can learn one representation that will cover a very broad distribution of shapes by providing codes, and this is the work of DeepSDF, which I really recommend. Your own Vincent Sitman has also done really great work in this space. So going back to our expression, how can we go from this to a signed distance field? Well, I can neglect contact entirely, so that will get rid of my boundary conditions. It will get rid of my reaction forces. I can get rid of the robot, and that will remove actions. I can also get rid of making any sort of predictions. And so what I'm left with is just the geometry. Now, I can replace the argument of this function, p sub t, with a query in 3D space and assign to that query a distance value. And now suddenly I arrive at the signed distance function. So great. I have a signed distance function, but I have to make a bunch of assumptions. I had to get rid of, I can only do 3D geometries. There's no force. This is static. It's not making predictions. There's no action conditioning, and there's no boundary condition, it's boundary condition unaware. And so let's put all the structure back into it to get a very nice sort of a representation for compliant tools. How are we going to do this? This is the key idea, the key message of this part of the talk. We're going to try to learn deformation fields from vision and touch. And so here is the signed distance field. I'm taking a crosscut of this geometry. This is a signed distance field. Blue indicates far, red indicates close to the surface. Here's the signed distance field, again, a crosscut of it, for this geometry. Here I've made contact and I've bent the shape. What I'm going to do is learn a deformation field that if you add to this field will give you this field. That is the main idea. And what I'm going to do is I'm going to condition that deformation field on the reaction forces, on the robot actions, on the boundary conditions. That is the main idea. And so one specific implementation of this idea is a representation we call Virdo. What we're going to do is we're going to take our reaction forces, we're going to take robot proprioception, and a summary statistic of the boundary conditions, C sub t. We're going to predict a force code and an object code. What we're going to do is predict a deformation module's deformation vector field. So here are deformed points. If you add the vector field to them, what you end up with is the geometry of the nominal shape. We're going to pass that through our object module and recover the signed distance field of the nominal shape. That's this thing. Great. We can also make this predictive by taking our force codes, an action, and predicting future reaction forces, predicting future summary statistics of the boundary conditions. This is just one implementation of the idea that I showed you in the previous slide. There can potentially be other ones. This is the best one that we could come up with. And so we can train this by having a robot grasp a compliant tool and noodle in the environment. Here's some examples of some spatulas. There's also a chain. Once you train your model at deployment time, here is the robot holding a spatula. It's going to be performing a policy, and we're going to be doing state estimation. On the left-hand side is the raw RGB values. On the right-hand side is my point cloud coming from a PhotoNeo. And what you can see is that the spatula is disappearing behind the P's. It's making contact with the environment in ways that you cannot see from the visual feedback. The purple overlay is showing for you our estimation of the deformation, and we can also estimate where the contact is also being made with the walk. Here we know the geometry of the walk, and we're just doing state estimation against that geometry. Here's that same task with the second stroke. It's a bit more fun because the spatula really disappears quite far back here. But you can see that we can still maintain an estimate of the pose of the spatula, its deformation, and the contact boundary conditions. Cool. Here's an example of the chain task where we're hiding a part of the chain by these Cheez-It boxes and these mustard boxes. And that purple is representing for you what is currently the best estimate of the robot for where the chain is. And what's kind of cool here is that sometimes even the chain will rest on the table. The robot can also pick up on those details as well. Nice. So how does this work? How do we do state estimation from these partial views and just that proprioceptive tactile feedback? Well, if this is my deformed geometry and this cone represents my partial view, here's what I get to see of it. There's a partial point cloud, there's my reaction wrenches, and there's my robot configuration. What I can do is essentially backprop through my representation, fixing the network weights, and just optimizing over my summary statistic for the boundary conditions. By doing this iteratively over maybe 60 epochs in this particular example, you can recover the summary statistic and infer what the object geometry is. This is some of our older versions, so this is running at about 2 Hertz. We can get this to run at about 10 Hertz at this point with some simplifications. And so another really cool feature of this representation is that you get dense correspondences with no supervision. We're not supervising correspondences, but this is just something that naturally falls out of it. So here's my nominal shape. I'm bending in a bunch of different shapes, different geometries. And we've colored it so you can visually maintain the correspondences yourself, and it works pretty well. And now you may look at this and be like, OK, so how well does this really work? So here's us really bending the spatula really aggressively. This is done in sim because practically it's very hard to bend the spatula like that. This visual is a little hard to see, so let's zoom in. This is the spatula with a little bend, moderate bend, and almost folded entirely. You'll see that up to this point, the reds are matching up, the green and yellow and blue, they're all matching up nicely. Once you really bend it very far, you'll see the red has migrated to the middle of the spatula a little bit. There's more purple at the tip. The reason for this is that our deformation vector fields have a bias to having minimum distances. So it's inefficient for the representation to try to map these points all the way around. It'll map them through the spatula. So yes, there is a limit to how well we can maintain correspondences, but within reason, it does pretty well. Now, the way that we infer contact is a little bit involved. Here is the zero-level set of this function, that purple. But this function is defined over the full 3D space. And so what I can do is I can push the points that belong to the environment through that same representation. They will return a valid distance value, s. If that s is greater than 0, it means no contact. If s is equal to 0, it must also belong to the surface of the object. And if s is less than 0, then you have penetration. That probably suggests that your model is wrong and you should collect more data to fix it. But it's a nice way to diagnose. Now, the problem is this is kind of a two-step inference procedure. We do an inference procedure to summarize, get that summary statistic C sub t, and then we do this inference procedure to estimate contact locations. That's a little bit challenging, so let's try to fix that. Our fix is this algorithm called NDCF. The idea is to not only predict signed distance fields, but also to predict contact fields. A contact field is a value between 0 and 1, telling you for that query in 3D space, what is the probability of it being in contact. If 1, it's in contact. If 0, it's not, and everything in between. And so cool, we have this. The architecture looks largely similar to the previous model. Inference works just the same. And we trained this one in sim. The main reason for that is that it's very difficult to collect contact patches in the real world. This is collected in Isaac, where we do some tuning for the Young's modulus and for the Poisson ratio to match as closely as we can the sponge that we have in the real world. Here, the robot is grabbing this blue sponge and just whacking it into different geometries. As you're going to make contact, you're going to collect a whole bunch of data. You're going to train a model. And in sim, this is sort of evaluation. This is the partial view that we get. These are our reconstructions. These are our baselines reconstructions. And on the far right-hand side is ground truth. Now, sim is all fine and good. Do you really trust sim? I don't know. Here's how we evaluate in the real world. We came up with this kind of a quite clever setup where there's an acrylic plate. There's a photoneo behind it, which provides very high-quality point cloud measurements. And we just jam the sponge into it. As you jam into it, you know where the acrylic plate is. And you can measure quite precisely what the contact formation was. And so we can measure essentially how well we're doing in predicting contacts for flat planes. Here's an example of the partial point clouds that we're given. You can notice that they're very partial. There's a lot missing from them. And just from the reaction force of the wrist on these partial views, these are reconstructions of geometry and contact locations. On the far right-hand side is a comparison against ground truth measured by the photoneo. And you can see that despite having such a very little observation of the sponge itself, you can do a pretty damn good job of estimating what the contact patch was. At least I think. Now, we tried interacting with other geometries. Here's an example of a mug where you can see here's the estimate of, again, the deformation. Here's an estimate of the contact patch. Slow. There we go. And it seems to be doing a pretty good job considering the relatively poor partial view. But it's not perfect. There are some issues with it. So here's a number of examples where it doesn't work necessarily as great as you might imagine. So here's the handle, and what we'd expect is a relatively small contact patch over here, but you see that it's predicting kind of a long, wide one. There's a little bit of a bias in our data set for predicting more elongated contacts than short ones. It's a data set bias issue. It could potentially be resolved, but it is an artifact that you can see over here. it doesn't also fully comply in this particular example. It is doing quite well in the bowls, though. And what's nice is that you can actually diagnose it and figure out what's wrong with it and actually improve it. And you may say, OK, this is kind of cool. But what can we do with contact patches? Well, our goal was to kind of come at this from this extrinsic contact servoing idea. We want to write model predictive controllers that act on continuous contact patches. And so if you can predict a continuous contact patch, you can have an MPC control that will try to track it and perform a task. So here's an example of basically us trying to scrape off this gunk. We're describing the task in this red region. This red region is a contact formation. And what the robot is doing is it's running an MPC controller trying to have the spatula maintain contact patches along this trajectory. And if you can describe it in cool shapes, you can get it to have this interesting dodging behavior where it just dodge this obstacle over here. This is an example of how you would use these contact patches in an MPC controller. Now, you might say, OK, this is kind of difficult. It's not necessarily super intuitive as a human to define contact formations and contact patches for tasks. So can you alleviate this issue? Can you make this a little bit easier? And our answer is yes. Given in this work called Calamari, what we did is essentially came up with an approach that takes it in as an image as input. It also gets a command from the human, such as wipe out the dust. And it will produce a sequence of contact patches that it can pass onto our MPC controller. And so here's a number of, this is how it works. So for every point in this space, we have a contact over a spatial action map. We say what should be the value of the contact. 0 is 0, no contact. 1 is make contact. And then what we do is try to track it with our model predictive controllers. So it's entirely trained in sim and zero-shot transfer to the real world. And here it is generalizing across a wide distribution of backgrounds and tools and, I guess, bins. And here's generalization to wiping tasks where we have different formations of dots and button pushing tasks. And so what I hope I've convinced you of is that these multimodal neural implicit representations are a really powerful tool for compliant tool representation. They're really useful, and we should not really be afraid of compliant tools. Historically, people have complained, they're hard to represent, but I don't think that's really true. With these kinds of things, we can make a lot of progress. But now switching gears, I'm going to talk a little bit about our tactile perception and control with compliant sensors work. So some of you may be familiar with these sensors already. These are the soft bubbles that are now being actively maintained and developed by TRI. And the working principle is that essentially there's a latex membrane that is inflated with air. There's an acrylic plate behind it. And there's a camera that perceives the deformations of this membrane. Here's Mikhail's fingers kind of pushing it to show you convert a tactile signature into a 3D point cloud. And so what's really awesome is that these are compliant sensors. So they allow you to have gradual force buildup. They allow you to do a lot of contact-rich manipulation. They're very high resolution and informative, which is super cool. But they are compliant sensors. So there's a lot of deformable object stuff in here. And when I say they're compliant, here's sort of a visual to kind of illustrate for you what compliance means. This marker was originally held vertically. I moved and hit the 80-20, and it kind of tilts about 20 degrees. That's a significant amount of in-hand relative motion that we have to account for as we're performing a lot of our contact-rich skills. So what is our goal? Our goal is to control the object's pose and force transmission. And what we're given is joint torques. We're given membrane point clouds, and some notion of the object geometry that you're holding. What we're interested in is computing the robot actions such that we control the object pose and the force transmitted to the environment. And so the key insight here is to formulate the control problem like this. The cost is a quadratic cost. It's a pretty kind of a standard kind of a cost if you've done LQR control before. X is the concatenation of the geometry of the object, so poses, and the force transmitted to the environment, which is a vector. But what's interesting is the constraint set. You can see that that one equation to rule them all has shown up again here. We're going to replace it with its explicit form. So we're going to just try to predict future deformations of the membranes, future reaction forces. And we have a second constraint here, which is our observation model. Our dynamics model is entirely in the membrane space. Our observation model takes membrane space and maps it into configuration space of the object. And by having this decomposition, having these modular dynamics and observations, You get better generalization. You can do really effectively a lot of different tasks. And it's just switching out modules, you maintain your control stack pretty effectively. And so what does the observation model look like? That on the left-hand side is what we get from the sensors. We can convert them into deformed point clouds. We can compare the default point clouds to the nominal geometries, extract contact imprints, perform some sort of a constrained ICP to extract poses. Here's how it works in practice. Mikhail's handled the robot and marker. And as you can see, you can track the orientation of the marker. We cannot track its pose uniquely. Anyone know why? Just from tactile? It's symmetric, right? It's axisymmetric, so you won't know where along it you've grasped. You only know orientation. So how do we resolve that? Whack it into the environment. I know where the table is. So I just take my spatula, whack it into the table, and now I can tell you that's the contact location illustrated in red, and that's the pose of the tool in my grasp. Super handy. It'll do another whack. And again, contact is really useful, again, for disambiguating these things. OK, so what does our dynamics module look like? We're taking these tactile imprints. We're taking reaction wrenches. We're taking the pose of the robot, and we're trying to predict the future values of those things, conditioned on the robot action and the tool that you're holding. And what's insightful here is a tactile encoder and decoder. These are responsible for taking these high-dimensional tactile signals and crunching them down. The way that we do this in practice is these are shared across all of our tasks. So the robot, as it's manipulating things with these tactile sensors, we're going to take all those tactile signatures and learn the tactile encoder and decoder first. And then we're going to learn our dynamics models. And our control stack looks pretty much like how you'd set up a classical MPC controller. You have your membrane dynamics models. You can sample these things with robot actions. And this is, again, MPC, so you're going to sample a sequence of actions, see what membrane geometries you get, run your observation models to try to find object poses. And you're going to tune those actions such that these object poses and forces transmitted to the environment are the values that you want. And so now I'm going to show you a sequence of examples of the implementation of this idea. This is the simplest example. So the task here is keep the Allen key horizontal. The control is super simple. It's a kind of a kinematic controller, just to evaluate how well this thing works. And Mikhail is aggravating the robot and is continuously trying to compensate. Here's a bit more of a fun example where the task is to draw triangles. On the left-hand side, we've turned off the controller. On the right-hand side, we have the controller on. And there's a little bit of a reset as well. And as you can see, when we turn off the controller, your triangles look horrible. The marker slipped. Everything's gone to hell. You have your controller on and your little reset, and you draw these beautiful, repeatable triangles. Life is great. Now, that was kind of a little bit easy in the sense that we could reset at the vertex of the triangle. So what if we try to draw the longest line we can? Here's the robot trying to draw a really long line. And as you can see, as it's drawing, the marker is slipping. And it's continuously trying to adjust this graph to maintain the marker being as close to vertical as possible while maintaining contact. It eventually gives up at some point. Here's a bit more of a complicated task. We're doing in-hand pivoting. The robot is grasping the spatula. However, it's in the incorrect configuration. It should be aligned with the green. And so again, with just running MPC, it's going to plan for a sequence of actions, do a little bit of a readjustment of the grasp, and success. And here's another fun example where we're trying to do dense insertion. Here the tool is this box. And what you're trying to do is trying to jam this box into this opening, into this cavity, just from tactile feedback. What's interesting here is that there's not enough room as is. You have to force apart these two boxes such that this thing can go in. We're aware of the fact that there is like a sponge here and a sponge here. There's a little bit of compliance. So the robot knows that a priori. There's an initial image that the robot takes to localize these features, and that's it. We turn vision off. The rest of this is completely blind. The robot will go down, grasp the object. The pink is the pose estimation coming from our pose estimation algorithm. The red you'll see kind of pop up here. This is where it thinks contact is being made. It's a little noisy, but it's going to try to use this in its MPPI controller to plan for a sequence of actions. Again, jamming, and once it's confident, it will go down. That yellow is to indicate success, and it will go and repeat this again. Delightful. One final example that I'd like to show you, this is tactile cart pole idea. I think this is like a very nice and interesting benchmark task we came up with. If you're into control theory, the cart pole is probably your best friend. And so we thought to ourselves, what is control theory a la tactile sensing cart pole problem? Well, it's this thing. There's a cart and a pole. The cart is actuated by a motor you can see down here. And the idea is that the robot is tasked with keeping the pole vertical, subject to perturbances from the cart. And what this is supposed to simulate is as you're using a tool, you're often going to be adversarially pushed against by the environment. This is supposed to be a simulation of those adversarial tugs against you. And so it's a very nice way to try to evaluate different tactile controllers. This was constructed in the context of our most recent work on geometry aliasing aware controllers. So as I mentioned before, there is this effect of aliasing in tactile signatures. So you want to come up with representations that are somehow robust to this aliasing effect. This was some of our work that builds on that idea. And so the key takeaway is that tactile control of compliant sensors is really an instance of the compliant object manipulation task, and that we can perform very rich closed-loop control through just contact with these multimodal representations. And so what you saw here, the first thrust was our compliant tool stuff and the tactile perception and control. In the first thrust, we were doing compliant tools, but the grasps were quite fixed and rigid. And we had vision, but our tactile feedback was just proprioceptive. There's no tactile sensing. The second half was we were now using rigid tools, but in compliant sensors, and we had no vision. What we're working on now is getting the best of both worlds, trying to do compliant tools with compliant sensors, having vision and high-resolution tactile sensing, and having human-friendly goal specification. And so to give you the idea of a few things that I'm really excited about, really interested about and working on, we've been reproducing the GelStim sensors in my group. Here's an example of the GelStim sensors. And we're trying to do a nut and bolt assembly task. Again, trying to exploit a little bit the compliance that these sensors provide, although at a much smaller scale with respect to the soft bubbles. Here you get alignment. The robot is confident it's aligning. It will go back and then try to do the scrolling task. What you may have noticed in all of our work is that everything was with a single arm. But that's not necessarily the case. That's not necessarily how we interact with the environment, and it's kind of limiting. So we've spent a bunch of time working on doing in-hand pose estimation using dual arms. So the fact that I have two arms, even though both of them are using an unknown object, can be an asset to you. By just poking them against each other, you can use the information mutually from the two arms to infer the pose of both objects. This was work published both at IROS and RSS. And we're also graduating to trying to use vision and tactile for pose estimation. So here the red dot, the green dots are coming just from the soft bubble tactile sensors. The purple are coming from our vision-based sensing. And by merging these two point clouds in clever and interesting ways, you can resolve the pose of the screwdriver grasped by the robot in effective ways. And so this is a flavor of the kinds of things that we're getting into now, we're really excited about. And with that, thank you very much. We can do questions. Oh, sorry, yes.
Yes, just the last
Can you use the microphone, please? Just so that we have it on the recording.
So just in the last video, do you use information of the object to fuse the vision and the tactile?
Yes.
Okay.
Yeah.
Would you be able to do that without knowledge about the object? Like,
We're trying to now. I don't have a straight answer for you. We're trying to now. In principle, it should be possible. What's kind of interesting about this problem is I kind of glossed over a lot of the details, but the noise profile you get from your visual feedback is very different from the noise profile you get from your tactile feedback. Noise from vision is a lot more aggressive in some senses. Tactile is deeply interesting because the contact patches we get from the soft bubbles aren't actually the contact patches. They're just points that satisfy criteria for most deformation. That's not the actual contact. That's fake news. So what we're also working on is a representation that will actually try to recover the true contact patch and not this thresholding thing that we're doing, which is kind of nonsense. So that's kind of, those are some of the initial problems that we have to resolve before we can fully fledged do this problem correctly. But yeah.
Okay,
I feel like you
thank you.
said something else. I apologize. Did I miss the other half of your question?
No, I don't think so.
Okay, good. Whew. Yes.
Thank you for the talk. My question is regarding the first half of
Sure.
the talk. So you use the deep SDF, something like that, and then from there you can predict kind of which part is changed or not. And so does the model only is optimized for each object? That means that it cannot generalize to any other objects? Because I feel like the chain is quite different from the spatular, so I wonder how it is trained, whether it is trained some kind of within one data set, or whether it is optimized to one object.
Great, both really great questions. So what we do is generalize across classes of objects that have relatively similar geometry. So there's one model for a bunch of different spatulas. So we can generalize across spatulas that look vaguely like these ones. There's one model for the chain examples. It's not one model to rule all of them. But yes, you can get some generalization. So that's your second question. The generalization within distribution of the kinds of geometries you've seen. But it doesn't have to be just one. It can be many within that class. The other half of your question was DeepSDF. The only thing that we share with DeepSDF is this part. This is DeepSDF. It's in fact also Siren, FCNN, occupancy nets, all flavors of computer vision, sign distance function learning, they all learn this part. Everything else is what we do to make it work for compliant tools in robotics.
Thank you. Just a quick follow-up question.
Sure.
Regarding the spatular, is there any performance difference between the trained spatular and untrained or new spatular?
Oh, yeah, on completely new spatula, we tried it. So it depends on how, there's two things that our model kind of, one that does well and one that does not do well. The one that it does well is if sort of the composition of the spatula is similar, it'll do a fine job in. But if you kind of make the spatula like all, so a lot of our spatulas have relatively rigid handles and relatively compliant ends. If you made a spatula that was super compliant, it would not do well because it's very difficult to detect from just visual feedback whether two spatulas are like the same from a mechanical perspective or not. So one of our ideas is to try to make a conditioning here on some notion of Young's modulus and Poisson ratios to try to disambiguate, but that's not been implemented. So you can totally fool us if you give us two spatulas that look the same but have completely different mechanical properties.
Thank you so much.
Yeah.
Yeah, thanks. Yeah, okay, I can go? Okay.
Yeah.
Yeah, thanks for the talk. Yeah, so I just have some curious on the bubble gripper, like control part. So I realized that the bubble gripper is like changing the grasp pose, like varying the grasp pose, like strong grasp, like a less strong grasp. Like for example, in the final slide, the thank you slide.
Yeah.
Yeah,
This
so
one.
is that like part of the control loop or is it like a heuristically
No,
designed?
it's part of the control loop.
Oh, okay.
The
Got
action
it.
space, so the action space is SE2 plus opening, closing, and effector.
Got it. So the model that you learn like has some notion of grasping force as well.
Yeah.
Okay, that's great.
That's actually like super painful, by the way, because what ended up happening is that you have to collect data to be able to do this, right? So you hand it a spatula and it will drop it. And you hand it again and it'll drop it. You hand it again, it'll drop it. And it's kind of hard to pick up the spatula with these bubble sensors like when they fall. So someone has to actually get up and hand it back to it. So we could definitely be a bit wiser, but yeah, that actually caused us a huge headache, but we're happy that it was part of our control loop.
Yeah, I definitely feel the pain. Yeah,
Yeah.
thanks for clarifying.
Just wanted to ask a clarification about the diagram that you had in the slide you just showed before this,
Sure.
with, the first project.
Let's see. Sorry. Give me one moment. There it is.
There you go. So what are the inputs that go into the deformation module?
It's a notion of the object that you're holding, so an embedding of the object. That's the alpha term. And a force code is basically taking the proprioception of the robot, the reaction forces of the wrench, and that summary statistic of the boundary conditions, and crunching down into like a vector that is 128 dimensional.
So the force code also goes into the
these two
I see.
both go.
That's what I
And
missed.
this is a hypernet. So we tried a bunch of different ways of doing this. One way is to have that arrow go this way and have it be like a more traditionally conditioned model. Another way is to make it like a hypernetwork where this network will predict the weights of this network. We found in practice that the second version worked way better. It gave us more flexibility in terms of generalization. There's something else I want to add here, that these representations, these network modules are super simple. They're all ReLU. We tried the Siren version, which is all sine waves. We tried FCNNs, which is like a Fourier transform followed by a bunch of ReLUs. They work really well for single geometries. If you just want to optimize for one spatula, it works well. But they produce these horrible optimization landscapes when you want to generalize across a distribution of tools and distributions of scenes. So in practice, we found the dumb thing actually worked better than the more complicated, fancy things.
And then one more question about this slide. Is there a temporal aspect to this diagram? Or this is one single shot?
This part is single shot, and then that part is the temporal part. So this is predicting future parts. This is all responsible for resolving the current time. So this is all our perception stack, trying to figure out the geometry and contact location. That part is our prediction stack.
But there's no like tracking in the perception stack where it's using previous information somehow? Or
that's a separate story. That's a Bayesian filter that we run on top of it. So it's just a particle filter that we run in the latent space in C sub t. So you can maintain a distribution and make it temporally consistent by basically passing it through the network as a dynamics module. Like the most abstract way to think about this is ignore all this complexity. It's just taking in these numbers and spitting out almost the same set of numbers. And it's just xt a xt plus 1. And we're running the filter on the f of xt. Great, thank you.
I wanted to ask a question about the realignment. Did you try it with constrained environments? For example, in kitchen, you don't have a lot of space to work with. So were you able to like test it out in like really constrained spaces?
That's a great question, and the answer is we haven't tried. That's actually the thing that we're going to be doing for the next 2 years. Very specifically because I think that there's a lot of value in it. As you said, like natural environments, there's two kind of common features. There's clutter and there's affordances. So the affordance here is the entire table. If I put a wedge here, the top of the wedge could be an affordance for the pivoting as well. The hard part there is trying to figure out what you're allowed to pivot against and what you're not allowed to pivot against. Not all clutter is created the same. Jesus, that is hard to say. So trying to figure out what clutter is useful for you to do a task and what is not is actually the hard part. And I'm not sure how much of that is a perception problem versus what we've developed here is kind of what we're trying to figure out now. But yes, you're right. That is a problem that we are interested in trying to fix.
Nima, thanks. I want to go back to the basics and just ask more of a clarification, I think. So at the beginning, the starting point for part 1 is that we cannot do FEM, we cannot do particle-based, because maybe for FEM, we don't know a lot of parameters of the FEM model. But I wanted to understand that part a little bit better, because at the end of the day, if you provide a lot of data to the learning-based approach, I mean, you could use the same data to identify a lot of information for the FEM model. So it's just a computational reason not to go for the FEM?
No, that's a great question. I'm really glad you asked, and I'm glad someone asked. That's a really good one. So FEM classically has been designed such that it's an analysis and design tool, and so it needs a lot of its parts pre-specified. And so you specify boundary conditions, you specify a meshing, you specify parameters like Young's modulus, Poisson ratio, blah, blah, and then you can just run it. Out comes strains and stresses, which you can convert to forces. Inverting, what we have is often the boundary conditions that are the input to that model are hidden from us. Parts of that mesh are also hidden from us, and so setting it up with partial views is very challenging. It's not just an issue of data, it's just foundationally setting up that FEM when you don't see part of your object is really hard. The other part of the story is that most of these FEM solvers, the general case ones, are not backward differentiable in a clean way, and so you won't be able to figure it out in sort of a gradient optimization scheme. There's another challenge, which I didn't really have time to get into, but there's effects like shear thinning. There's like these really interesting mechanical engineering style continuum mechanics issues with FEM. For example, if you have a long cylindrical object that is compliant and you try to push down, we tried this in Isaac, it keeps blowing up. This is actually a known problem in FEM solving. It's just something to do with like long elongated cylindrical things. What we happened to be really interested in at the time was elongated cylindrical looking things. So we were having a super hard time trying to make this work in Sim. So we've tried Isaac and the FEM solvers from that. We've tried MATLAB's FEM solver. They've all just been a huge pain to get to work in any sort of a scalable way. Yeah, that's kind of where we ended up being at.
Right. Thanks.
Maybe one more. So I'll ask a question, then I'll take the mic to you. So just
And
building on.
Terry wants to grill me too.
Yes, everyone will grill you. Don't worry. So just building on what Luca was saying. So I'm curious if you found a lot of issues with ISAC in terms of how good the contact model is in simulation versus reality.
Yeah, that's a great question. It's hard to quantify, right? How do I tell you a number, right? I don't know how to tell you a number. We tried, and so for the NDCF stuff, it produces plausible enough deformations and contact patches that they kind of look like they could explain the world. But I just don't know how to quantify that gap. We, in fact, just wrote a loss function which took in essentially the point cloud representation of my object in Sim, the point cloud that I could perceive of the object in the real world, took a chamfer distance loss. We also measured the reaction wrenches of the wrist of the real robot and the fake robot, the Sim robot. And the way that we infer the Young's modulus and the Poisson ratio is literally by doing gradient descent on that loss function to tune those things. That's about the best that we could say. And then we can tell you how good that prediction is in terms of chamfer distance losses, contact patch chamfer distance losses, and reaction wrenches. But those numbers don't really mean anything. They're just a number, I guess. Sorry, that was not the most satisfying answer. This is the best we could come up with.
Hey, Nima.
Hey, Ryan.
I really like the work. I had a question about specifically the bubble gripper sensing. So, like, how reliant is it on like the known structure, like you're grasping a cylinder for when you're trying to detect like external contact detection, and the fact that like, oh, you know, it's going to be along the axis of the cylinder, and like, how much more ambiguous could you make the features without having to rely on additional sensing beyond what you're already doing?
Those are both great questions. It's intimately tied to knowledge of the type of object you're holding to be able to do those extrinsic contact estimation stuff. There's not much. My general philosophy is like the more detail you want out of your model, the more information you should be willing to give it. And so that's one of those things where you have to accept that. Ambiguity is a really great question. We have a current project on trying to learn mutual information between tactile sensors. And so if I give the same thing to two sensors and I have them both grasp it, can you tell me how much mutual information there is between them? The soft bubbles are pretty good, actually, I would say, in terms of most of the things that we've been interacting with, but you can definitely fool them. One way to fool them is to like just give it a big blob thing that is like almost cylindrical, but close to a sphere. It definitely has an orientation, but it'll be hard to detect if it's big enough. So there's adversarial geometries you could totally come up with to confuse it. The way that we actually confuse it in the current work that we're doing is giving it L shapes. It'll get confused over those, giving it stars, and it's supposed to. It's just trying to figure out like where are the limits there, really, which is, I think, kind of interesting.
sorry, just one clarification, which is after you learn a velocity field, do you like integrate the particles forward, or do you update the sign distance function on like a grid based on advection?
Is that pertaining to
the first, I think?
Yeah.
Or rather, like I was curious how expensive the procedure is. Once you get the velocity field, updating the SDF or the particles.
It's almost instant. It's super fast. It's a vector field of deformation. So per point, it predicts how should that point migrate such that you recover the other geometry. And it's just a process where you take, this is a collection of tensors, and you're just adding a collection of tensors to the output of a network forward pass. It's a really efficient procedure. The whole thing, forward passing, is really efficient. You can do it really, really fast. The inference is the part that takes us a little bit more time, where you have to do basically backprop through the network several times. In most cases, it might take about 20 to 50, 60 backprops. That's where we're kind of starting to hit the bottleneck on speed and inference. But again, I love this way of doing inference. It gives you like a grounded way to give me full deformation despite heavy visual occlusion. It's expensive, but it gives you a lot of information that you don't have from just raw visual feedback.
All right, thank you.
Thank you.
One more question.
Do it.
I wanted to ask you about the wisdom of using shape or geometry or assigned distance function as representation from where to extract deformation. It seems to me like intuitively, if I think of how do we do that, it seems like there's a lot of rich information in looking at sort of like how locally texture deforms. That's something that you sort of are giving away in some way if you're looking at it from just geometry. Like imagine like
local texture, like how yeah.
You have a thin layer that you stretch, and locally has the same shape.
I see.
But you could see texture, like color, for example.
Yeah.
Have you tried like feeding all RGB images to these networks or different combinations for how to extract deformation?
I've been opposed to the second half, and I'll tell you a little bit of an answer for the first half, I guess. I've been sort of intellectually a little bit opposed to just feeding RGB into it because it's a different type of data. This is geometric 3D reasoning, and that one's color, and I want to have a nice way of making them to talk to each other in a clean way. Just dumping it in, I don't feel like is very intellectually satisfying. But the texture side of the story is we have some ongoing work, which is not public yet, but hopefully soon, where we try to actually detect texture from touch as we graze over things with these things we call nanopillars. They're like ultra-thin pillars you make essentially the size of like microns. And they can give you a lot of information about texture feedback, which I think will be a huge addendum to this thing. It'll make it work a lot better. Definitely, we're missing a lot, and this definitely needs to improve in many ways. I'm not as excited about that as perhaps I am about generalizing this to multi-sign distance fields playing with each other. So if I have this compliant spatula and I want to touch a compliant like ball, that's a really interesting geometric problem that that has nice constraints. It's a nice way to play with things. Yeah, so texture is super important. Not clear how to plug it in. RGB, a little bit more clear, but still not clear. Multi-SDF representations, super cool.
Any last questions? No. So this is the way we welcome you, Nima. I think this is the longest we have grilled any speaker.
That's great.
So,
this is what we do here. We grill people.
Yes. So welcome back, and thank you again for the wonderful talk.
Much.